Hypersonic Shadow: Truth and Myths about the secret SR-72 project. When rumors first surfaced in the early 2010s about the development of a hypersonic aircraft known as the SR-72, they sounded like something out of science fiction. Journalists, analysts, and even aerospace experts treated the reports with a healthy dose of skepticism. The idea that anyone was seriously pursuing a manned or unmanned aircraft capable of reaching Mach 6, twice the speed of the legendary SR-71 Blackbird, seemed almost absurd. Yet, over time, increasingly credible evidence began to emerge. Subtle hints in Lockheed Martin's reports, a confirmed partnership with Aerojet Rocketdyne, patent filings, and funding at the Pentagon level. Even the silence from the U.S. Air Force was seen as a potential sign that something truly revolutionary was taking shape in the shadows of classified research labs. So as America once again quietly leaped ahead of the rest of the world into the hypersonic era, right before our eyes, but in total secrecy? In this video, you'll find out. To understand where the SR-72 came from, we need to look back at its legendary predecessor, an aircraft that still inspires awe among aviation enthusiasts and military professionals alike. The SR-71 Blackbird was far more than just a Cold War reconnaissance plane. It became a symbol of American technical audacity and undisputed aerospace dominance during the 1960s and 70s. Its design looked like something torn from the future and dropped into the middle of the 1960s. The jet black fuselage, elongated body, pointed nose cone, and sleek delta wings appeared almost otherworldly, but every line served a purpose in coping with the extreme aerodynamic forces of flying at Mach 3.2, more than 2,175 miles per hour, or roughly 3,500 kilometers per hour. At the heart of the aircraft were the one-of-a-kind Pratt & Whitney J58 turbojet engines, which essentially transitioned into ramjets at supersonic speeds. They burned a special fuel known as JP7, a substance so thermally stable it could be ignited with a match. To reduce the infrared signature of the exhaust, chemical additives were mixed into the fuel. These were early steps toward what would later become full-scale infrared stealth countermeasures. The SR-71 also laid the groundwork for stealth technology in its most primitive form. Its radar-absorbing skin and minimized radar cross-section allowed it to penetrate deep into enemy territory, slipping past dense radar networks while leaving only ominous contrails in the sky. Its unique titanium construction featured corrugated skin, which might sound absurd for a supersonic aircraft evoking images of an old shipping container. But in the case of the SR-71, it was a stroke of engineering genius dictated by the extreme conditions of high-speed flight. Flying at over Mach 3 caused the aircraft's fuselage to heat up to several hundred degrees Celsius. Under such intense thermal stress, a smooth fuselage would have expanded unevenly, leading to cracks, popped rivets, and structural failures. The corrugation's fine longitudinal ridges on the skin allowed the metal to expand and contract along both the length and width of the aircraft, without tearing. Yes, the corrugation's slightly compromised aerodynamic efficiency compared to a perfectly smooth surface, but at hypersonic speeds, aerodynamic drag is primarily influenced by the aircraft's overall shape rather than surface texture. And at cruising speed, thermal expansion effectively smoothed out the surface, making it nearly flush in flight. The cockpit windows of the SR-71 were built with multi-layer thermal protection to withstand the hellish temperatures encountered during flight, and its navigation systems were far ahead of their time. It used inertial gyroscopic compasses and astro trackers that aligned with the stars, but even the most brilliant engineering feats don't last forever. In 1998, after nearly 3 decades of service, the SR-71 was finally retired. The main reason was the staggering operational cost. A single hour of flight cost the U.S. Air Force approximately $200,000 to $250,000, factoring in preparation, maintenance, and refueling. The aircraft burned around 8,000 gallons of JP7 fuel per hour, roughly 30,000 liters, with each gallon priced at about $8 or nearly $2 per liter. That meant fuel alone cost more than $60,000 per hour. And that was in dollars of the 1960s, when you could buy a brand new 1965 Ford Mustang, a legendary muscle car with a V8 engine, for just $2,500. In contrast, today you'd pay around $25,000 for a basic Toyota Corolla. Each SR-71 also required an enormous support crew and specialized infrastructure, including its own dedicated tanker, the KC-135Q, which was uniquely modified to handle JP-7 fuel. By the late 1980s, a new era of space-based reconnaissance had arrived. Satellites could gather strategic intelligence from orbit with no risk to human life, far lower costs, and the ability to monitor targets around the clock. Orbital intelligence gathering proved to be simpler, cheaper, and politically safer than conducting hypersonic raids over hostile territory. And now, years later, a new silhouette emerges on the horizon, no less intimidating, even more mysterious: the SR-72. Why is it needed? Over time, military strategists realized that satellite reconnaissance, while powerful, is not omniscient. Satellites operate on fixed orbits, which are well known to adversaries. That means enemy forces can anticipate satellite flyovers, hide mobile missile systems, relocate key assets, jam active equipment, or simply suspend suspicious activity. The SR-72, like the SR-71 before it, would be unpredictable. It could appear at any time, fly in at blazing speed, collect vital data, and vanish before the enemy even realizes it was there. In today's conflicts, decisions are made in hours or even minutes. Satellites with their pre-planned orbital paths cannot offer real-time tactical flexibility. The SR-72, on the other hand, could respond instantly. It could detect a missile launch, identify troop movements, scout ahead of an airstrike, or even carry out a strike on its own. This capability becomes especially critical in so-called A2AD, anti-access area denial zones, where traditional drones are shot down and manned aircraft face extreme risks. In the early 2000s, within the walls of Skunk Works, the same top-secret division of Lockheed Martin that once gave birth to the SR-71, discussions began about its successor. This gave rise to the concept of the SR-72, not just as another aircraft, but as an unmanned reconnaissance strike platform capable of flying at 6 times the speed of sound and executing missions that push the limits of physics. To achieve this, Lockheed Martin partnered with Aerojet Rocketdyne, a leader in jet and rocket propulsion systems. Their shared objective was to create a power plant capable of operating both at subsonic and hypersonic speeds. This led to the revival of the scramjet concept, a supersonic combustion ramjet engine in which air is compressed and burned without ever slowing below supersonic velocity. This is no longer science fiction, but a new stage in engineering evolution. However, the path from concept to reality was blocked by a major challenge: speed range. Turbojet engines perform well up to about Mach 2.2, but become ineffective beyond that. Ramjets and scramjets, by contrast, only become functional around Mach 3 and above, so how do you bridge the gap between the two? The answer was TBCC, turbine-based combined cycle. This is a hybrid propulsion system where a turbine engine handles takeoff and landing, while the scramjet activates at high speeds. All of this is integrated into a single housing with a shared intake and nozzle, but with separated airflow channels. It's a technology that flirts with the limits of plausibility. This marked the beginning of a new chapter, the development of the SR-72, the son of the Blackbird, a machine with the potential to redefine not only aviation, but the entire concept of strategic deterrence. Creating the SR-72 is the pinnacle of aerospace and propulsion engineering. Hypersonic flight is nothing short of a journey through hell. At speeds near Mach 6, the surface temperature of the fuselage exceeds 3,600 degrees Fahrenheit, over 2,000 degrees Celsius. That's not just heat, it's an environment where aluminum and even most steel alloys would melt. Any miscalculation in the design and the aircraft would simply incinerate in midair. Engineers found themselves facing challenges previously seen only in the design of intercontinental ballistic missiles and space shuttles. The materials used in the SR-71 were no longer suitable. Titanium melts at much lower temperatures. A new solution had to be found. They turned to high-temperature carbon ceramic composites, the same materials used in the thermal shielding of the space shuttle and the re-entry vehicles of ballistic missiles. These materials not only endure extreme heat, but also maintain structural integrity under high-speed stress and G-forces. Technologies from the deepest layers of the defense sector were brought into play: ultralight thermal protection coatings and multi-layered fiber-reinforced panels capable of withstanding even plasma flow during high-speed flight. Every component of the SR-72 must do more than just survive, It must remain functional for prolonged periods in conditions that would melt even heat-resistant steel. For many years, the SR-72 remained little more than rumors, speculation, and anonymous leaks. But in 2013, that changed. Lockheed Martin officially confirmed it. They were working on the Blackbird's successor, and not just working on it, they were building a machine that would be twice as fast as the legendary SR-71. The target was a top speed of Mach 6, a next-generation hypersonic reconnaissance and strike platform. What finally made it possible to move from theory to practice was the emergence of 21st century technologies. If the SR-71 was designed on paper with drafting tools and slide rules, the SR-72 is being developed entirely in digital space advanced computer simulations, aerodynamic modeling, and most importantly, additive manufacturing. 3D printing of parts from heat-resistant composites and metals that would be impossible to craft using traditional methods has become the key to turning this concept into a real flying aircraft. Engineers also drew on the experience gained from working with the Falcon HTV-2, an experimental hypersonic missile designed to test the most extreme flight conditions imaginable. The Falcon served as a kind of flying laboratory where engineers explored aerothermodynamics, flight control, navigation systems, and stability at hypersonic speeds. It was during this phase that Skunk Works embraced a new motto, one that would become the guiding philosophy of the entire project. Speed is the new stealth. In an era where radar systems are becoming increasingly advanced and air defenses are denser than ever, the only way to break free from a tightening noose is to move faster than anything can catch. The SR-72 is designed to cut through hostile airspace so quickly that the enemy would only have time to ask themselves, "What was that?" In 2018, the project received another round of confirmation. Lockheed officially declared that the son of Blackbird, as the SR-72 is unofficially called, was no longer just a theory, it was becoming reality. The company emphasized that advancements in 3D printing, digital modeling, and automation had made it possible to keep costs within a manageable range and significantly accelerate development. But the SR-72 isn't just about speed, it's also about offensive capability. The aircraft is expected to carry hypersonic weapons, most likely missiles, that could strike targets hundreds or even thousands of kilometers away. This is more than just a reconnaissance platform, it's a hypersonic fist, capable of delivering a lightning-fast blow against high-value, heavily defended targets. This ambition brings a new challenge. How do you launch missiles at Mach 6 when the fuselage and the surrounding air are both glowing hot? It's a technical nightmare, but Lockheed has a compelling precedent. Back in the 1960s, they successfully launched missiles from the YF-12 prototype at speeds exceeding Mach 3. If they could do it then, why not again? The SR-72 then is not merely a spy plane, it's a tool of strategic deterrence. Early reports suggested that test flights could begin as soon as 2025. That date sounded bold, both a promise and a provocation. But as the scale of the technical and organizational challenges became more apparent, timelines began to shift. Today, most experts point to 2027-2029 as a more realistic window for the prototype's first flight. The SR-72 is already embedded in the Pentagon's long-term hypersonic strategy and is receiving funding from the federal defense budget. Exporting such an aircraft is virtually out of the question. Unlike the F-35, which is actively sold to allied nations, the SR-72 will guard America's most sensitive strategic secrets. Advanced materials, proprietary propulsion systems, cutting-edge navigation algorithms, and thermal masking coatings all make exporting even a limited version extremely risky. This isn't a weapon for coalitions. It's a weapon for dominance. What do you think about the SR-72? Can America pull off another miracle like it did in the early 1960s with the legendary SR-71? Let us know in the comments below. If you enjoyed this video, give it a like, subscribe to the channel, and hit the bell so you don't miss future stories from the world of cutting-edge military technology. What's coming next will be faster, higher, and louder.